When we write code, it's tempting to imagine it running in a perfectly controlled environment. We compile our work, run it through an emulator, and watch it execute exactly as designed, operating under perfect, sterile conditions. But successful compilation is only a baseline. It proves the syntax is correct, not that the application will survive in the real world. The reality of a mobile operating system is chaotic. We call this environmental entropy. The moment an application leaves the lab, it is subjected to unpredictable user behaviors, resource drops, and hardware shifts. Application crashes are not random accidents. A crash is a structural failure, the system's inability to process that incoming entropy. The quality of your application is defined entirely by its structural resilience against unexpected conditions, rather than how smoothly it runs on the happy path. There is a distinct line between amateur coding and professional software engineering. An amateur focuses on implementing features. A professional engineers for failure cases. The core mandate is straightforward. An Android app must absorb unexpected events without crashing. This isometric 3D model represents a standard application. It operates as a holistic data pipeline connecting the user interface, internal logic, local storage, and the external network. While this pipeline moves data efficiently, every connection point where information is ingested or requested acts as a potential vulnerability for system collapse. There are 5 specific threats constantly attacking these junctions: null data, network drops, missing files, revoked permissions, and database errors. Adopting a defensive architecture means we stop reacting to these crashes after the fact. We proactively build structural safety nets into these ingestion points before the failures can even occur. Let's isolate the internal logic layer first. This is where your variables process active information. Looking at this logic node, the vulnerability lies in expectation. It waits to receive a solid data packet to execute. What happens when that data doesn't exist? This is our first failure state, null data. The incoming packet arrives completely empty. This happens constantly in live environments. A failed API parsing event can strip a variable of its value. When that hollow packet hits an unprotected logic node, the system cannot process the absence of data. The node fractures, triggering an exception that terminates the application. Designing a system that relies entirely on perfect data continuity is a critical architectural flaw. The primary defense for the internal logic layer is strict data validation. Rewinding the process, we insert a validation shield upstream of the logic node. Now, when a null packet arrives, the shield intercepts it, recognizes the empty state, and safely diverts it. Internal system stability demands a pessimistic approach. Treat all incoming variables as potentially empty until a validation layer explicitly proves otherwise. Moving outward, we reach the application's external boundaries. This is where the app interacts with physical device storage and the internet. Focusing on the external network block, we encounter the second failure state, network failure. This connection relies on a steady data stream. Mobile devices constantly move between cell towers and Wi-Fi zones, making them highly susceptible to a sudden severing of connectivity mid-transfer. If an active network request drops and the system isn't prepared, the application threads will hang, resulting in an immediate exception and termination. The defensive tactic here is graceful degradation. The app should automatically fall back to background retries or local caching. Watching that failure again with defenses in place, the severed connection instantly reroutes the data request to a local cache node, keeping the user experience uninterrupted. This brings us to the third failure state, missing files on the device. Local device state is highly volatile. Users can unmount SD cards, and the operating system can aggressively delete cached files to free up memory anytime. You cannot assume a file is exactly where you left it. You must verify its existence and availability immediately prior to executing any access commands. Whenever an app interacts with a boundary, the architecture must assume the external environment is actively hostile and unreliable. Finally, we need to examine the operating system layer, where the application negotiates access to hardware and local databases. This introduces our fourth failure state, permission denied. Many developers operate under the dangerous misconception that user permissions, once granted at installation, are permanently available to them. Modern operating systems give users total control. They can revoke access to the camera or location dynamically while your app runs in the background. To defend against this, the architecture requires dynamic state check-in. You must verify permission status every single time a hardware API is invoked. And right next to hardware access is the fifth failure state, database errors. If a read or write operation fails, an unhandled database error will cascade backward up the pipeline, directly striking and freezing the user interface. Local databases are complex ecosystems prone to index corruption, thread deadlocks, or unexpected timeouts that completely halt data retrieval. By installing a fallback interceptor, we trap the database error before the cascade happens, keeping the user interface block active and responsive. Stable integration with the operating system requires building systems that survive the sudden, unannounced revocation of critical resources. Our mature architecture pipeline is fully reinforced. Under a stress test, a null packet is safely deflected. A severed network reroutes to the local cache. Missing files and revoked permissions are halted, and an intercepted database failure keeps the interface completely intact. The application survives this barrage not because the environment is safe, but because the architecture successfully absorbs and neutralizes the entropy. Application crashes are rarely random anomalies. They are direct failures of developer anticipation. Mature Android development is, at its core, an exercise in defensive engineering. Making the app work for the normal case is merely the baseline expectation. Ensuring the app survives the failure cases is the professional imperative. Building an unbreakable app requires a relentless focus on every single data ingestion point, constantly asking, what will fail next? Designing for failure is not an optional feature to be added later. It is the defining standard of professional software architecture.